Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Plastic Today webinar, how a leading injection molder implemented rapid tooling to slash lead times for its customers, sponsored by Mantle and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few announcements before we begin. First of all, this webinar is designed to be interactive. The dock of widgets at the bottom of your screen will let you learn about today's speakers, download resources, share the webinar, and participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event, and toward the end of our webinar, we will ask you to complete our survey. Just take a minute to fill this out before leaving us. It helps us make these events better for you. And lastly, if you're experiencing any technical problems, just click on the help widget found at the bottom of your screen or type your question into the Q&A area, and we'll be glad to offer one-on-one assistance. And now on to the presentation, how a leading injection molder implemented rapid tooling to slash lead times for its customers. Discussing today's topic is Ethan Rideout, Director of Marketing at Mantle, Eric Derner, Application Engineer at Nicolet Plastics, and Brian Torres, Chief Commercial Officer at Nicolet Plastics. And to learn more about our speakers, just visit the speakers widget. Ethan, thanks. Over to you.
Awesome. Thank you for that introduction, and excited to be underway here. Excited to be joined with Nicolet Plastics, both Brian and Eric, as well as we're talking about how they have implemented rapid tooling to really slash lead times and involve their business. A quick agenda for today, and again, feel free to ask any questions throughout. We'll be happy to take all those questions. We're going to start by just a quick introduction to Nicolet Plastics, who they are, what their business is. We'll talk about Nicolet Plastics and their journey with 3D printing in general. We'll talk about Nicolet Plastics and tooling. We'll do a quick introduction to Mantle's technology and Mantle 3D printing, and we'll talk about how our technology works, specifically how it was designed specifically to produce injection mold tooling. I have a couple inserts on my desk here today that we'll be talking about and looking at. And then lastly, we'll be talking about how the impact is actually adding value at Nicolet, and look at some examples of how they've been using the technology and a few other examples as well. So with that, I'll turn it over to Brian here to tell us a little bit more about Nicolet and their operations.
Good afternoon, everyone. So Brian Torres with Nicolet Plastics. I am the Chief Commercial Officer here. And a little introduction about Nicolet Plastics. Tooling is very much at the heart of who we are and who we continue to be. And so our humble beginnings started in 1976 as a tool maker, and over the years transitioned into an injection molder, as well as continuing our tooling efforts in 1985, which is when Nicolet Plastics was founded. Through the years and changed ownership, ultimately Nicolet Plastics was purchased in March of 2017 by a family-owned business that's very much a staple in the Wisconsin area. The family was looking to diversify their ownership and ultimately decided to kind of start up a manufacturing arm of the family business. And that's really when True Venture Composites was established. And ultimately, Nicolet Plastics is the first manufacturer within that family ownership division. And so we are located, all three of our facilities are located in Wisconsin. We have a facility that is in Jackson, Wisconsin, which is about 20 minutes north of Milwaukee. We have a facility in the center of the state in Ripon, Wisconsin, as well as our facility in northern Wisconsin, about an hour and 15 minutes northwest of Green Bay. Our newest facility is the facility in Ripon, Wisconsin, which currently is set up for injection molding and will fuel our growth, but is not yet up into full production. So if we go to the next slide to kind of give you a little bit of a breakdown of the different facilities. What's unique to Nicolet Plastics is we really don't try to be everything to everyone under one molding facility. And that's really the breakdown of our soon to be 3 operational facilities. And so starting with our Mountain facility, we very much focus on lower production volumes with high mix and complexity. So we've got 22 presses ranging from a 30-ton machine all the way up to a 610-ton. We're about 40,000 square feet. And the unique part about this facility is that we're doing right around 20 tool changes a day. So you can imagine some of the complexity and the short-run nature of our business that makes up our Mountain facility. A lot of highly engineered resins. We are both UL certified as well as ISO 9001 certified out of this facility. And this facility is where we house our full service tool room as well as the Mantle 3D printer. One unique part about the Mountain facility is that about 30% of all the manufactured SKUs within this facility receive some type of post-mold operation. And so whether that be plastic machining, vibration welding, sonic welding, pad printing, general assembly, we do a lot of those post-mold activities in our Mountain facility. That then takes us to our Jackson, Wisconsin facility. This is almost the opposite of what our Mountain facility is. And so this facility is really dedicated to high production volume, low mix, low complexity. We've got 22 molding machines ranging from a 50-ton all the way up to 250-ton machine. Here we're doing around 3 to 4 changeovers a day, mostly commodity resins. And we are on our path to an ISO certification. So we utilize the same quality manual as our Mountain facility and are on our journey to ISO compliance in June, July of 2025. Our third facility that, like I said, we recently purchased in the past 2 years. Our Ripon facility is kind of a blank slate. Of the 54,000 square feet of space, we've got about 15,000 square feet ready to go, and that's the picture in the lower left corner. Depending on what sizes, we think we can get up to about 40 machines there. We are exploring clean room for medical and or food molding applications. We are utilizing this space for warehousing so that we can take advantage of more bulk purchases of resin and different components. And Nicolet Plastics, we also have our own truck. So we've got a nice milk run route between our 3 facilities that allows us to take advantage of some of those larger purchase quantities to deliver just in time to our manufacturing facilities. And so this is very much a flexible space. Like I said, it will fuel our growth into the future. But ultimately, we have great flexibility on what this facility becomes based on the type of work that we ultimately bring in. And so kind of transitioning to what we feel is one of the advantages in working with Nicolet Plastics. Our team has extensive tooling knowledge. All of our project engineers are plastic engineer degreed. And so they're not only the ones that are managing the programs and the timelines, they're also able to provide, material recommendations, design recommendations, all have extensive tooling knowledge. And so the day-to-day person you're working with on your project has that extensive plastic and tooling knowledge. We pride ourselves on fast quote response. It's not out of the norm for us to turn around quotes within 2 or 3 days, including the tooling. For certain quotes that require specialty inserts or a specialty material, it may take us a little longer than that. But by and large, our average is about 2 to 3 days for a quote turnaround. Mentioned part design recommendations. We do have an entry-level mold flow analysis in-house. When we have projects that require more of that, we often partner with the Beaumont group to take us through more in-depth mold flow analysis. But we provide our customers with DFMs, production print reviews, and ultimately the earlier we partner with our customers, the more value we find in what we provide to them. And so, like I said, with material recommendations, design recommendations, the earlier we get involved in the project, the more value we can bring to the table. We do have 3D printing capabilities with a carbon 3D printer that we brought online in 2019. We utilize this machine primarily for verification, prototype plastic parts for our customers. We actually also have some customers that their volumes are so low that they don't really warrant the investment into a tool. And so they will actually order plastic production parts off of our carbon 3D printer. And the really nice thing that this allows us to do is really partner with our customers through the process. So not only can we produce prototype fit, form, function samples off the carbon printer, but now with the Mantle technology, it allows us to print rapid prototyping tooling, which we'll get into in a little bit. But with this technology, it allows us to provide our valued customers parts within hours, not weeks, in a traditional molding environment. And I mentioned the fact that our tool room is in our Mantle, Wisconsin facility. That facility supports our tooling needs for all three, well, two of our current operating facilities, ultimately all three of our facilities once we get up and running. We've got 6 full-time journeyman tool makers on staff, capability of managing rather large projects, up to and at times over 100 total tools. We do some of our own complete tooling builds from the ground up, continuing to do more and more of that with the Mantle technology. We also outsource some of our tooling both domestically as well as offshore. But by and large, we're doing almost all of our mold builds, engineering changes, maintenance, repairs, modifications in our Mantle, Wisconsin tool room. And so with that, I'm going to pass it over to Eric Durner, who is our technical sales engineer here at Nicolet Plastics.
Good afternoon, everybody. So some of the challenges that you run in with tooling is a lot of people see out there in the real world is long lead times. And along with that comes the high costs. And the prototype tooling, yes, it's challenging. It's just, hard to do very cheaply and very quickly these days. And again, it's also hard to, find experienced tool makers. They're not around anymore. They're like gold. So if you have some good ones, please hang on to them. So that kind of leads us into, why did we choose Mantle? Introduction to Mantle. Mantle allows us, to make production tool in actual prototype time. Think about it. If you're thinking about making some plastic parts and it's like, I really need to test this in an injection mold tool, we can now make that tool within 2 weeks. And it's actually a good production grade tool. We're talking H13 pre-hardened steel here for tooling. Most of the inserts that we print with, when they come out of the machine, they're anywhere between 75 and 95% complete. Obviously, you still got to do some waterline tapping and clean up ejector pin holes and do some final fittings, on some of the shut-off surfaces. So again, it's dramatically, reduced our lead time. And with bringing the Mantle machine on, I kind of think of it as a three-quarter journeyman tool maker, right? They're doing all the magic behind the scenes. This thing is going by itself. It's been a great addition to Nicolet Plastics. Go to the next slide. So, it is expanding our business. We're trying to get involved with our customers quicker because we're able to offer them some of the prototype solutions they're looking for. Some of the other things that are really good eye openers now with this process being from a platform up type manufacturing process is we can offer conformal cooling where we couldn't, do it before effectively and cost effectively. It just comes part of the package now with building a tool from the platform up. You can just automatically add the conformal cooling. Again, producing high complex parts. That's kind of where the Mantle machine really shines itself. Something I would actually call it, a core making machine where you have a lot of ribs and stuff that you traditionally burn with an EDM and really complex geometry. That's where the magic of this machine really, really shines. Again, looking at this chart here, we're on a downward trend of tool makers here in the United States. So, we had to look somewhere and we started looking at technology, and that's kind of pointed us in the Mantle direction.
Awesome. Thanks, Eric. I know we'll get back to you in a little while here to talk through some of the use cases, but quickly I want to chime in here and share a little bit more about Mantle and how it works. Mantle at our core has a technology that was designed to automate your toolmaking processes. We do this by printing precision mold components with really unmatched accuracy, surface finish, and tool steel performance, with the real value being that it eliminates much of the time and cost of a traditional toolmaking process, like Eric just mentioned, that those EDM steps, the rough milling steps, the EDM, wire EDM, and the programming involved, all of that being eliminated and automated with the technology. And one thing that's very, very unique to Mantle is that our technology was designed specifically for printing injection mold tools. It's the only application we target. It's the only application we do. All of our customers are using it for printing injection mold inserts. We're not doing rocket parts or medical parts or anything like that other metal 3D printing companies are doing. The only thing we're printing today is injection mold inserts, and that's what our customers are using. And to do that, we knew the requirements for injection mold tooling were quite stringent and quite difficult, and we really designed our technology to deliver on that. In terms of surface finish, we see a 1 to 3 micron RA, a Termi 26 or a D2. I don't know, Eric, what you think, but we often compare it to a fine sink EDM finish. I don't know if you can chime in on what the finish on a Mantle insert would be in comparison.
Yeah, that's about really what it is. I mean, you can really get down to the final finish steel even with just rubbing a 400 grit stone on it. It polishes out really, really well.
Yeah, that's a good thing to add is that, of course, it can be polished up to those mirror A2 finishes if you need to, but, as printed, you're kind of getting that matte surface finish, holding a thou per inch tolerance, really, really sharp, crisp details, EDM sharp features, which we'll talk about how we accomplish that, flexible designs to enable things like conformal cooling, like Eric mentioned, stable, durable, well-known tool steels. We're not printing some material you've never heard of. H13 tool steel is really our mainstay, as well as 420 stainless steel. And the technology is super, super easy to use. It's not some really complex system that takes a PhD to run. I'd like to say we could teach anyone on this call how to use it in a matter of an hour or so. Another thing that's really, really important, and I'll ask Eric for his thoughts here as well, is how compatible it is with standard operating procedures where, we did mention that it gets you that 75 to 85, 95% of the way there. Often there's a need for some grinding, some finishing of ejector pins, polishing, texturing. And Eric, has your tool room found that these inserts are pretty easy to work with generally once they come out of that process?
Yeah, it's basically like taking a block of tool steel off the shelf. It's, it's chemically identical right down to the molecule level. So there is no difference in your machining operations that you traditionally do. One thing I would like to add is, with the Mantle technology, after it's printed and then goes into a sintering oven, you can now think of your mold block as being thermally stress relieved at a 95% complete. So as tool makers know, every time you touch a tool to a tool block, you're adding stress to this. So you're actually getting a more thermally stable material block when you're done with the Mantle process.
Yeah, absolutely. And just to share, a quick example, and we'll look at a lot more examples later on. This is just a small little core insert, but they ran over 200,000 shots, was produced in only 2 days here with a 65% cost savings, and everything was accurate within a thou here. So it's one thing to have some fancy technology and some specs like we were showing before, but we'll show a lot more examples later on and kind of comparing them to what the traditional tool making process would look like. So quickly, I want to walk through how this technology actually works because it's pretty unique compared to any other metal 3D printing technologies. We're really combining a couple of different things here, which is printing, extrusion, CNC machining, and then powdered metal sintering processes. And I'll walk through each of these different steps. But essentially, our technology is comprised of 2 pieces of equipment: the printer, which you're seeing there on the bottom, and then the furnace. And these different steps are happening in these different machines here. All of this, of course, is controlled by the software. This is a question that we get quite a bit: is how do I program this machine? What CAM software do I need to use, etc. Our software makes this super, super easy to do. You don't need to have any programming experience. You can really get up and running in just minutes. And it's going to generate all the tool paths for you. So both of these machines are run by the software, and this makes it super, super easy to use. We won't talk too much about software today, but I just wanted to add that in because it's one of the most commonly asked questions we get. So to start talking about our process, we have to start by talking about paste. Mantle is very unique in that a lot of metal 3D printers, they print powders, they print filaments, they print rods even. With Mantle's technology, we're printing a paste. You can see it on the left there. That paste is very similar to a toothpaste in terms of consistency. It's a viscous paste. And what this paste actually is a combination of metal powder mixed with solvent and binder. So we mix all of those ingredients together and it comes in a tube. And that's actually what we're printing in our process. So we start by just simply printing a layer of this paste. We're just extruding it out of a needle like you're seeing here on the left. The solvent makes the material viscous enough that it can simply flow. It can easily just be extruded out into the place that you want it. After each layer is printed, we go through and dry that layer. So what's happening here is that the solvent is actually being removed out of the layer, leaving up behind just metal powder and binder. And lastly, one of the most important steps here is the actual machining step. So every single layer, we're printing a layer, drying a layer, and machining a layer which is why if you look at our parts, which I wish everyone had one here in their hands, you can see the features are super, super crisp. You're getting those EDM sharp features. You don't see layer lines or anything like that. You're getting this excellent surface finish. And that's because every single layer is being printed, dried, and machined. This is happening over and over and over again, and also enables us to do these really, really deep ribs and deep features that traditionally you'd have to do sinker EDM for, because it's print, dry, machine, print, machine over and over and over again to build up a part, allowing us to do these really, really high aspect ratios, really small parts. I'll show a video here in a second just because it's a little bit hard to comprehend sometimes, but all three of these steps are happening inside of this one machine, all happening inside of the printer. And I'll show just a quick video here walking through the different steps. You'll see it starting by just simply extruding that paste material. It's not even being heated, it's viscous enough to just extrude it out, print a layer, go through and dry that layer. So that's removing that solvent out. It's firming it up so it's firm enough to be machined. And then it goes ahead and is machined. We're using standard cutting tools here. So our smallest tool actually is a 6th thou ball and mill. So some really, really small cutting tools. You can see the shapes are refined, improve the surface finish, add features that couldn't have been printed. This is going to repeat over and over and over again to build up the part. Let's finish here. Awesome. So once printing is complete, then we go into a furnace. What's happening in the furnace is a sintering process. This is very similar to what happens in a metal injection molding process or binder jetting process, where the part actually shrinks inside of this furnace. The metal powder actually fuses together, the part densifies and comes out as a dense, strong metal part. So the part does shrink about 9% in this process in the furnace. Our software, of course, accounts for that. And even with that 9% shrinkage, we're still able to hold that plus or minus 1 thou per inch, which is really, really challenging generally in other sinter-based processes where they're shrinking more like 18, 19, 20%. So after printing is complete, you put the part into this furnace, it's going to run. And then what comes out is your dense, strong tool steel components like I'm holding here. So, all in all, you can see there's these kind of 4 major steps to this process. And what's really, really important to know is that this technology was designed specifically for this toolmaking process. It's designed to deliver the features that are involved. One thing that actually is pretty cool is that our smallest tool actually used to be a 20 thou ball and mill. We got feedback from people like Nicolet and other customers saying, "Oh, I wish we had smaller, get closer to an EDM sharp." Now the smallest tool is a 6 thou ball and mill. So a lot of advancements that have happened to really make sure this technology is what our customers need for the tool making process. Now we'll go into talking about a couple of examples here. I know Eric has a couple of examples he wants to share from Nicolet, and I have a couple more to include from some of our other customers as well.
All right. So what I wanted to do with Mantle, or what Nicolet wanted to do, is we wanted to take a part that had some challenging geometry, right? Something that's not just an open and shut parting line, something with some steep angles on it, something that would have required some EDM time, and then something with a pretty much an open cavity, and even to the point to where we wanted to have a tool that, we need to put an insert in as well for venting purposes. So as you can see here, here's a couple of cavity blocks. You can see the multiple step parting lines. You can see the insert pocket there that was actually machined in with the Mantle process. And along with the core and cavity blocks that you see here, we also did print that insert block that fit into that pocket. We had about, I would say, 10 hours of final finishing time in there to make these blocks moldable. The insert pocket itself was in very, very good condition. We just needed to do some honing on the insert itself to fit in there. Traditionally, having to wire that with EDMs, doing multiple skim passes and things like that to get an insert to fit in there, relatively easy with the Mantle process. So all in all, this probably saved us in the hours of, I want to say, it took 4 weeks off of our lead time from this, taking it from 180 hours of machining down to about, 12 hours of actual machine time for the tool maker from a tooling touch point. At the end product was a nylon 6, 35% glass filled, as you can see there. We did have to do a little bit of touch-up work on the parting lines. Again, that's part of that, between 75 and 95% complete block. So all in all, this process went really, really well. I did challenge the tool room, change your thinking a little bit and let's try do the least amount of work on the core and cavity blocks as we can. Would love to get this out in the machine and just, from the first shots, I want to know what this process does. So they actually, went down that road, a little bit reluctant, of course, as tool makers are. We went out there and shot some of the first parts relatively, I would say within a half hour, we had parts falling into the box. A couple little areas we had to go back and touch up because there's a little bit of flash, but all in all, to get this part from concept to completion, in basically 2 weeks is pretty amazing. So with that, you can see all the steps here that we eliminated. Traditionally in tool manufacturing, you got the raw materials, you have to go through programming, and then you have to go through EDM. And, with the Mantle technology, we basically took out having to source the raw materials because that obviously comes with the Mantle machine as a paste. Spent the time designing up the tool, answering literally about 10 to 15 questions in the Mantle software and hitting cycle start, reducing all them subsequent steps, and then coming right into the final finishing part of the project. Second project that we worked on, kind of similar to the first one, multiple stepped parting lines, big wide open cavity, and then you can see all the detail on the core side of the tool. Another good fit for the Mantle process. A lot of EDM and that you'd see in some of the small rib pockets and things like that. Those were completely eliminated with the Mantle software and the Mantle process. So estimated this would take 8 weeks to build. We ended up doing this in 5 weeks. So you can see there was a 3-week reduction in tool making time there, but this was a relatively good size core and cavity block. So end plastic again in this tool was a 35% glass filled plastic. Similar to H13 material, warranted for up to 100,000 cycles. Again, same thing as the previous one, looking at the chart at the top, all the different steps it takes to make a tool. Using the Mantle technology, we pretty much eliminated all of them except for the final finishing process. Again, looking at what did we need to do with this tool. This one here, we actually incorporated conformal cooling in, trying to, get that cycle time quicker and quicker on the tool. And the option was there. Why not use that? Why not use the conformal cooling technology that's out there? It doesn't cost you anything anymore. So another great feature with the Mantle technology.
Awesome. Thanks, Eric.
You
just
bet.
going to quickly share a couple more examples from some other customers, and then of course we can take some questions and go back and look at other things. More on the OEM side from our customer Heiko, who makes these wire management components. Another really good example, similar to the last parts, in that really small ribs, parts that would require a lot of sinker EDM time. Conventionally, they were saying this would have had to have rough milling, a ton of electrodes made, squaring of the block, drilling and tapping of holes, a lot of sinker EDM time, wiring of ejector pins and burning of gates. With the Mantle process, they printed and sintered this, of course, with little to no time from their tool makers. They squared the inserts, they tapped the mounting holes, they finished the ejector pins, and then they burned the gates. So the really important thing here, though, and it's a pretty common theme, and I think it's similar to the parts that Eric was just showing here, is that the cavity detail, the EDM kind of features that would have required EDM, were left as printed. They didn't have to be touched, which generally we hear and we find are the most time-consuming and expensive parts of a tool build. So the ability to kind of leave those parts as printed and features as printed saved a ton of time on this inserts and a lot of different inserts we're looking at. Another good example here, just a little bit of some of the results of this part. All of the molded parts were functioned as expected, fit, form, and function were equivalent. They've shot over 1.5 million shots on this tool. They saved over 2 weeks, and they saved 60% of the cost compared to producing this tool traditionally. So just another great example of a really good fit for the Mantle process. Another cool component here, this is actually a threaded component. You can see that they needed to test a new thread design, and this is just some of the thinking that happens once you have a Mantle machine in-house. So they actually took an insert here and they cut a pocket in it, which is what you're seeing here. and they printed a few different inserts actually and placed them inside of those pockets to really take advantage of the Mantle process to really reduce the size as much as possible so it would print as quickly as possible. This printed in just 2 days. They left all of those sharp threads as printed and only required 3 to 4 hours, they estimated, of toolmaker time, which was squaring of the blocks and tapping of those mounted holes to actually tap to mount that insert inside of the insert. The result was they were fully functional MPT threads. They gauged and sealed properly. They saved over 2 weeks. This was for a new product development process, so they were able to really test these new threads, test this new design to understand, is this what we want to go to market with, or do we still need to do some product development and evaluation? Couple more examples here. This is actually a core component. So this was printed. One thing with the Mantle process is today that there's no support material, so we're not printing overhang features. So you can see that sort of core that went inside of this sort of pipe component was printed with that rib on the bottom, and then they went through afterwards and cut that off. They printed this component in just 3 days. They would have had to outsource this otherwise because the design was too complex for their internal tool shop to make. They saved 75% of the cost on this insert, as well as over 4 weeks. So another really good example here. And one last one here is just another really good example of all the EDM sinker time that can be saved. This had a 15-degree parting line, which made it quite challenging, as well as all these small, deep ribs. After printing was complete, they just did a little bit of finishing, which was squaring of the inserts and tapping the through holes. And then this saved over 40 to 60 hours of sinker EDM time, which was reduced. Switching over to talking a little bit more on the mold making side and the product development side. This is a part from Westminster Tool, a toolmaker located in Connecticut. They were approached by a leading medical device OEM to help them understand the prototyping process and the material compatibility process of bringing a new medical device to market. They were looking to get these production representative parts, meaning they needed these parts to be molded out of a steel tool. They didn't want to use aluminum. They didn't want to use plastic 3D printing. They wanted to know how these parts were going to mold in a production tool to validate that part function, understand the molding process parameters, and understand all of those processing parameters and cycles and things like that, and help with different material selections through biocompatibility testing. The part was very complex, required over 40 swipe by shutoffs, as well as the contoured parting line. Unfortunately, we can't show the actual part because it's still confidential, but this is just a representation of similar to what the part looked like. The process for Westminster Tool was to print these prototype tools in about 6 days. They said that this was fully unattended, less than 2 hours of active time from their team, because it's that simple to set up and get this thing running. Sintering, it was about a 42-hour sintered process, so about a day and a half. Then the final finishing work, which was 2.5 hours, about 55 active hours, which was squaring the blocks, hard milling some of the primary vents, wire EDM of the ejector holes, tapping water lines, and hard milling just a couple of the difficult swipe by shutoff areas. But ultimately what the result was, they were able to deliver production representative molded plastic parts to their medical OEM customer in just 4 weeks. This was a 50% lead time reduction, down from 8 weeks down to 4 weeks. They saved 110 hours of active manufacturing time compared to traditional manufacturing, and they delivered to their customer over 7,000 pieces of ABS and a PC ABS blend for that medical customer to do their biocompatibility testing. One thing that's not on this slide that's also really important, though, is that because they did this prototyping work and evaluation work for this customer, they were ultimately able to win the production order as well, which was for a much bigger tool, a much more expensive tool. But if they hadn't been able to do this, early development work for them, they wouldn't have gotten that same exposure, which ultimately allowed them to win that production order, which is something we see on the molder side too, of being able to get involved early in the development process, in the prototyping stages, et cetera, thanks to Mantle's rapid tooling process to ultimately allow you to win some production business. One last example here, and one question that we get all the time is about durability of our material. People often think about 3D printing, they think about prototyping, they think about quick turns, low volume stuff. This is just one of our best durability examples. This is a core that's actually used for molding the thumb screw inside of a deodorant stick that actually advances the deodorant up. This was done with Tessie. They've run over 1.65 million cycles on these inserts, and they're still running with no signs of wear. These have some S7 shutoffs on them that are quite abrasive, and they didn't see any unexpected wear here. Even with printing too, they were able to produce these weeks faster than conventional machining. So over 1.65 million cycles, that number's going up every day. and those inserts are still running in a production environment in a big 32 cavity tool here. So just one quick example of some of the durability that's possible. And with that, we'll go ahead and switch over to some questions. I want to thank you all very much for joining us and giving us this 30 minutes out of your day. We'd love to talk about your application, to see some of your parts, your tools, et cetera, to give you a better understanding of if you were to print those with Mantle, would you be saving time? Would you be saving money? Would you be using conformal cooling, et cetera? You can feel free to shoot me an email. I think you'll have our information anyways, or click that link there. Would love to talk about your application and how Mantle can potentially help. At this point, I see there's already some questions coming in, and we'll go ahead and take some questions. Thanks.
Terrific. Thank you so much. Great presentation. Appreciate it. But before we begin with the Q&A, I'd ask all of you to direct your attention to our webinar survey, which is available next to the presentation window. And if you close the survey, you can reopen the widget by clicking on the icon along the bottom of your screen. And again, thanks. Your participation helps us make these events better for you. And now on to our Q&A. As a reminder, to participate, just type your question into the text box located next to the presentation window, or click on that Q&A icon in the text box on the bottom of your screen. If we can't answer all submitted questions, we'll get an offline response to you after the event. So let's start. Our first question comes from Mohammed, who wants to know, I'm wondering if you're using metal-infused plastics for printing these tools.
Yeah, sure. So it's not a metal-infused plastic as much as it's a metal paste, essentially, which is metal powder, binder, and solvent all mixed together. And what's really important is that the final result is just metal. There's no binder left. There's no solvent left. All of that's removed throughout the process. And what's left is sintered metal, which is essentially, it's metal. It's metal powder that's been fused together through a sintering intensification process. So we are not using a metal-infused plastic. We're using a metal paste that is then sintered in a furnace to densify and remove anything in that paste that wasn't metal.
Okay, thank you. Keep the questions coming. This one comes from Charles, who wants to know, along the same lines, what materials can be printed?
Sure. So today we're printing H13 tool steel and 420 stainless steel. Those are mostly on the H13 front right now. It's kind of the workhorse of injection molding. I don't know, Eric, you guys are mostly using H13, right? As far as I know.
Yes. Mostly H13.
Yeah, H13 tool steel and 420 stainless steel. The 420 is something actually that's at the tail end of the development here and should be available very soon. But we got a lot of requests for the 420 stainless steel from the medical device community, which is a big fraction of our business.
Terrific. Thank you again. Keep them coming. This one from Gordon, who wants to know, what's the maximum size?
Yeah, so this is a great question, and that's something I should have included here. So the size of the actual build of the printer build volume is 8 by 8 by 6. That's in inches, or I think that's 200 millimeters by 200 by 150. But one thing to consider is our tolerance is scaling with size. So it's that plus or minus a thou per inch. So on an 8-inch part, it's gonna be plus or minus 8 thou. So we see that really the key value and the best size parts are kind of in that 5 and 6 inch range and smaller. They also tend to take longer to print the bigger they are, of course. So we kind of see that key core value in the 5-inch range, and also a bunch of customers who are being creative and really understanding how to insert an insert or cutting down insert size. We just gave a webinar actually last week on optimizing parts for the process. It turns out, really just printing as small as you can, of course, really sees bigger cost and lead time savings, and trying to find ways to incorporate that with traditional machining, which is really good at making big shapes, but isn't good at making complex stuff like we are.
Okay, great. This question comes from Lloyd, who wants to know, are the cutting tools standard, or is there something custom you need for the process?
Yeah, that's a great question. So all of the cutting tools that we use in our process are standard off-the-shelf carbide tools. We offer a recommendation. Eric, I don't know if you can chime in, or Brian as well, of how long our tools last in use. This is something we get, but since the material is very soft, there's very low cutting forces, so we're using off-the-shelf standard cutting tools for our process.
Yeah, I don't think they've changed the tool out since we've loaded them up, since the machine has been delivered. It's pretty crazy.
Yeah, essentially it's a paste, right? So it's almost like machining a foam material. So you can machine very quickly. Really, we can use these really small cutting tools like the 6 thou ball and mill. But they are just standard off-the-shelf tools that we obviously have suppliers that we recommend, but you can source them from wherever.
Okay, thank you. Keep the questions coming. Again, we'll get to as many as we can in the time we have left. Alan would like to know, what CAM software do you need to use for this process?
Yeah, so we have our own software that technically it is a CAM software, but it is very different in that it's very plug and play, where you click a couple of options and it's going to generate all those additive and subtractive toolpaths for you. Eric, I don't know if you can chime in on how you found the software and how it would compare to a traditional CAM software.
Well, yeah, comparing it to traditional CAM software is, you don't have to pick all the, the geometry faces and surfaces and things like that. I mean, it's just, it does it automatically, which, in my mind is difficult to comprehend, but it just does. And Mantle continues to, push software updates. One of the updates that we asked Mantle for is, there are certain cases like on shut-off surfaces and things like that, is there ability to add a little bit of stock on that when we're going through the user interface. So actually Mantle pushed down a software update for us that you can now select certain surfaces and add a little bit of extra stock. There are times when you want a little extra insurance policy, especially when you got a lot of time put into the block, that you want to make sure that you get the correct shutoff put together and have enough press on those areas. So again, thank you to Mantle for, listening to your customers and shooting off software upgrades. You don't really know what you got until you get out in the public, right? And Mantle's been great listening to us. So breath of fresh air.
Yeah, great.
Terrific. Let's wrap up with this question from Evan, who asks, what is the hardness and durability of these printed inserts?
Yeah, great question. So one thing that's really important to know is that our materials are H13. They are 420. They're not some variation or things like that. The H13 is going to come out of our process at a 42 Rockwell HRC. If you need to, you can heat treat that using conventional heat treatment processes all the way up to a 52. But like you saw in a few of our examples here, we've had inserts run millions of shots and they're still running. But of course, that's going to be very dependent on the design of the insert, the resin that's being run, the temperatures, the pressures, et cetera. But we haven't seen really any inserts fail unexpectedly or anything of that nature. I mean, even when they do wear, of course, you can repair them and do anything you would do to traditional H13 to our material. So they're very durable. They're H13 tool steel, 42 Rockwell HRC. You can heat treat it all the way up to 52 to be used anywhere from prototyping to bridge all the way into production.
And that's all the questions we have time for today. I want to thank you guys. I appreciate your time and expertise on today's topic. Any closing thoughts before we wrap today?
I'll just say thanks for joining. Hopefully this was valuable, 30 minutes out of your day, and feel free to shoot us a note if you want to check anything out or if you want to get something made from Nicolet as well, of course.
Great. Thank you to our sponsor, Mantle, as well as to everyone in the audience. We appreciate your attention and participation in the Q&A. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may have not been able to join us live today. This webinar is copyright 2024 by Informa. The presentation materials are owned or copyrighted by Informa Markets, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests, Ethan, Eric, and Brian, I'm Michael Krieger. Thanks for your time, and have a great day.